Okay. Just a really quick recap on last time. We're looking at this thing called the viewing pipeline, which is the process that takes you from the abstract representation of the environment, which is inside the computer. And this is describing, well, no, sorry, this is even before that. This is the abstract representation of the environment, describing the structures and objects in the environment using vectors and planar faces and lines and so on. Even before that, you had the individual object spaces where the basic building objects are designed. Just, you know, a single world, so just a single object defined, and define it centered at the origin and roughly parallel to the X, Y, and Z axes to make it easy to plot the coordinates and so on. Then we do various transformations, which we discussed in this chapter last week, in how to pick these up and place them at various locations into the world. But then that's still kind of abstract. It's just kind of sitting in the computer's memory. Then the question is how to get it onto the screen. So at the end of this pipeline is the image, the two-dimensional image as displayed on the actual computer screen. Now that is done by, you know, the view presented to you on the screen is you're viewing from a certain point in the environment, looking in a certain direction. So we imagine a virtual camera that is placed into the environment at a certain point, and that's pointing in a certain direction, okay? So that would be like the P and Q that were specified in the, the P and C, the camera position P and the center of view vector C that were specified in the assignment there. So then we go to this procedure of alignment, which is, as we said, to bring the virtual camera to sit at the origin and to have the center of view, wherever it is, somewhere on the positive z-axis. Because the way the two-dimensional, the way the three-dimensional left-handed coordinate system works and the computer graphic conventions is that the x, so you got x, y, and z, the x and y are the horizontal and vertical coordinates on the screen, then the z-axis points into the screen. Okay, so positive z directions are into the screen, negative z directions are out, back at you out of the screen. Okay. So alignment is this process that standardizes everything, so that you're viewing the environment always from the origin, and the center of view is always on the positive x-axis. And that sets the world up then. So it's still a three-dimensional abstract world inside the computer's memory, but you're then ready to do some kind of projection onto the screen. And there are a few different ways in which you can carry out this projection. Ultimately, you want to do it so that it carries perspective information. So you have these kind of lines which are really parallel in reality, but are going to look like they're going to meet at some point. So you get this impression of perspective. So you can judge, you can get an impression of the three-dimensional nature of the scene, even though it's just on the two-dimensional screen. Okay. So these issues of projection to the screen we'll deal with in the next chapter. Okay. But overall, this process is referred to as the viewing pipeline. Okay. And then John Shiak in term 2 will take you through some more aspects to do. So even after you've done the projection, there's still more technical things the computer has to do. It has to work out, well, how much of the scene can you actually see? Because like, I can't see everything that's, you know, I can't see everything that's placed forward of this line from this plane from which I'm looking at, because certain things are outside my field of view. Can't see you guys now, okay? You could be doing anything to me. So there's a certain, there's a certain field of view, and that requires the environment to be clipped to a certain screen, okay? There's a certain angle that I can see, so to render that to the screen, the computer has to get rid of everything that's outside it, and it shouldn't show that. And then there's also the thing about worrying that some things are in front of other things. When it's projecting to the screen, when it's drawing things, you don't want it to start drawing this building back here or this main part of the church back here, say. You don't want to superimpose it over this house here because this house is in front of it relative to where you're viewing it from. So there's this idea of having to sort the objects into some kind of distance and obscure the ones that are behind other ones. It has to do that. Then there's even the very basic thing of how to draw lines across the screen, okay? Because the screen ultimately is some kind of array of pixels, and it's a non-trivial matter how to choosing which pixels to display in order to create the overall impression of a line. Okay. All right, so let's come to this idea of coordinate alignment then. So we'll set this up and we'll describe the sequence of transformations carefully, and ultimately we'll arrive at kind of formulae or expressions for the transformation matrices in terms of the data. So one thing we want to look at this is be clear on what the input into the procedure is. Okay, what are the givens into the procedure? What data do you have to work with? Okay, so we're imagining a virtual world, one made up of a few of these basic building types. So we're going to have a virtual camera, which will be located at a position with position vector v. And the center of view, the place where the camera is looking at, we'll suppose that that's given by a vector c. So v is where the viewpoint is, viewpoint or the virtual camera, and c is the center of view, the point at which it's looking at. So straight away then we can say, so these two, v and c, are the inputs. So the virtual environment is already there. So there's a collection of coordinates of vertices and, specifications for drawing lines between certain pairs of vertices and so on. That's the virtual environment. And then we have these two extra pieces of information, the viewpoint and the center of view. And out of those then straight away we can obtain the direction vector. So the vector which shows you the direction in which the camera is pointing. And that's going to be the direction vector which takes you from the point V to the point C. So that's this difference C minus V. Okay, D, the vector going from the point V to the point C. It's worth I'll switch to the. It's worth just just put a little reminder of that. So this is the viewpoint V here. C is over here. So just remember that D is going to be this. D is going to be the vector joining those 2 points. It's just some little sketch to remind you. Sorry, it's drawn in the wrong place. Some little sketch to remind you. To remind you the meaning of D there. Okay. So we're now going to do the alignment, and the output. So the input is like the environment itself, which will just be the collection of vertices, the collection of coordinates of vertices. So you'll have some gigantic matrix with loads and loads of columns, one column for each vertex in the environment. Each column will have 4 entries in it, 4 rows, be the 4 homogeneous coordinates of that vertex. Okay. So for a complicated environment, that matrix could be really, really long, because there's one column for every vertex in the environment. So it could be a huge, very long matrix stretching out the door there. We're going to assemble this 4x4 transformation matrix. The idea is when we simply multiply the 4x4 transformation matrix positioned on the left, multiply it into the long vertex matrix, that'll give you a new vertex matrix, which has the new positions of all the vertices. Okay, so let's start looking at some diagrams just so we can get a handle on this. Okay, so we're going to illustrate it, we're going to consider a virtual environment which just consists of this kind of arrow type object. Okay. This will be enough just to suggest the translations and the rotations that we're going to be talking about. Okay, so here we are. Yes, it's a 3-step process. First of all, there's a translation, okay? Because it's easy to take the viewpoint, the position of the virtual camera, and move it to the origin. All that needs is a translation. You just need to translate all the objects in the environment by the vector minus v. Okay. So prior to any transformations, you just got the virtual environment. This arrow thing is somewhere in the environment. Somewhere there's a viewpoint V, and somewhere there's a center of view, C. So C is maybe attached to that arrow object, but it could be any point in the environment. So to get our viewpoint down to the origin, we just slide everything. Slide everything so that V goes to the origin. So a translation by vector minus V. So you'll then be in this position where the viewpoint is now the origin, and this vector now is exactly this vector D we talked about. D, the vector V minus C. And this is the vector going from the origin to the center of view. So the center of view has now become the point D, the point with position vector D. Now the next thing we need to do is to, look at that, 1, 2, 3, is to do a rotation. To do a rotation so that the center of view is brought onto the YZ plane. So this is now the point with position vector D. It's sitting out somewhere over here, somewhere which isn't in the YZ plane. The YZ plane is this sheet defined by the Y and Z axes. So the first thing that's required to do is to do some kind of a rotation. It'll be a rotation by this kind of angle here, rotating things around the Y-axis. So the Y-axis is staying where it is, and we're just shifting the whole world, the appropriate rotation around the Y-axis, to bring D into some point over here, D prime, say, which is now in this XY plane. Okay, that's the first of a two-step rotation process to bring the center of view point onto the Z-axis. First of all, you rotate it so it's in the YZ plane, okay? And then that's one of our standard rotations, isn't it? Our rotation about the Y-axis, okay? And then we'll just need to rotate it down this way to get it down onto the Z-axis, and then it will be on the Z-axis as is required by alignment, okay? So in the notes there, you can see in figure 6.6, this shows or suggests what the environment might look like after this arrow type thing is taken and the whole environment is rotated around the Y-axis to bring the center of view to be within the YZ plane, okay? So the YZ plane is that vertical plane defined by the vertical Y direction and the Z horizontal direction, okay? So that's achieved with a matrix Ry. And then, suggests in this picture, you then have this new center of view point with position vector D prime. You then just need to rotate so that that moves down onto the origin. And that's going to be a rotation around the x-axis, one of these pitch rotations. Okay, just rotate the whole environment so that D goes down onto the z-axis. Okay, and that's kind of shown there. The effect of that is shown in figure 6.7. So you have those three transformations overall. I can't quite get them on the same screen. Taken from the general environment in the diagram up the top, translate it so that the viewpoint is on the origin, rotate around the y-axis so that the viewpoint is in the yz plane, and finally rotate around the z-axis so that the center of view comes down onto the origin. And again, we're performing that overall transformation, the composite transformation. We're building it up as a sequence of our standard types of transformations. And for us, those are translations in the three-dimensional space and the three types of rotations around the x, y, or z axis. Okay. So here's another, just a slightly more precise diagrams. And there's two particular views given of what's going on here. The first one is a top view. So you see in the diagrams going down the left-hand side, we're just looking down onto the XZ plane. Remember your X, Y, and Z plane. So we're looking down from a point, yeah, think about it, from a point on the positive Y axis. To go over here. The point on the positive Y axis over here, I have my thumb X and my middle finger Z. So I have X going up and Z going left. So it's arranged consistently. We're looking down at it from a positive point on the Z axis. We're looking down on it from above. The diagrams down the right-hand side show a side view. Viewed from the side, viewed from a point hopefully out on the positive x-axis. Well, no, that has to be the negative. We're actually viewing that side view, so that's viewed from a point on the negative x-axis. Okay, so I've got y and z as they're indicated in the diagram, but my thumb is going into the board. So this is the side view from out on the negative x-axis. I don't think I've said in the notes from which side it is, but okay, so this top view is from the y plus axis, you could say, from a positive point on the y-axis, and the side view is from the x minus axis. Okay, and you can confirm those by the use of your left-handed rule. You have to remember as well, thumb is x, first finger is y, and middle finger is z. Okay, so the first pair of diagrams is just the initial setup. So the arbitrary v, the arbitrary c, and this object somewhere in the environment. So first of all, we do the translation. Okay, so we translate everything so v moves to the origin. So in the top view, you have this new picture where the object is moved slightly up and to the left. But in the side view, this kind of drags the object down and to the left. And v goes to the origin. So now the object is kind of, part of it is in the positive y half of the plane, and part of it seems to be in the negative y half of the plane. Okay, but our center of view now at this point, it's out just in the general xz space. We want to bring it to the x equals 0 space. We want to bring it onto the yz plane. So that's a rotation, this rotation that's needed. Okay, to rotate around the y-axis, you think the y-axis is coming out here. So you want to rotate around this axis and just bring this back to here. So that's very easy to show in the top axis, in the top view, the view from above, because we're looking along the rotation axis. So this simply rotates down to here, so it's going to change the orientation of this. This object's going to be oriented something like that. Kind of harder to show in the side view, but doing that rotation, that might, you see this side of the object here, which we can't really see, this becomes exposed to us now when the object gets rotated around. Okay, so that was the rotation around the y-axis. Then finally, we do rotation around the x-axis, which doesn't really change the top view a whole lot, except maybe it changes the tilt of the thing. So we're now exposing some of this front face of the object, which we couldn't see from above before. It's a lot easier to see what's going on here in the side view, because you're rotating now around the x-axis, and it's the x-axis which is coming out and into the screen there. So this object is rotated down one click like that. And the setup is now in its standard way, ready for projection, okay? Because you have the camera at the origin, and the viewpoint is on the z-axis. So the screen, remember, is the xy plane. So the xy plane is located here along this vertical line, and it comes out like this. So the screen is kind of the computer screen that this environment will be projected to. It's the screen which is kind of normal to the screen of the actual screen, the projection screen you're looking at. There's too many things. So this environment would then be projected somehow onto this xy plane, which is the plane of the paper here, ready for rendering onto the screen. Okay. Now, there's the most basic type of projection can be done just by forgetting about the z coordinate. Okay, and if you forget about the z coordinate, that does the perpendicular projection of all vertices smash onto the xy plane. That's the most basic. It's the simplest type of projection to implement. Just lets every object here fall down onto the xy plane. What it doesn't give you is any kind of perspective information. There'll be no difference to how points far away from the screen or points close to the screen are projected. So any notion of depth is lost in that. Okay. So this is the kind of thing that you're asked to do in your assignments. So first of all, or next, we want to just look at this down to the level of the actual transformation matrices. Okay. So the first thing you're going to need is the translation matrix, and that's immediate to get what that is. Remember, what's the data into this process? The data is the environment itself and the vectors v and c. So from the vector v, you can read the components of the vector v and straight away form that translation matrix. That's the translation matrix in homogeneous coordinates for translation by the vector minus v. Yeah. Then we need to rotate around the y-axis, and the picture for that is shown up there. Now, rotation about the y-axis, from what we've done before, rotation around the y-axis by an angle theta, anti-clockwise when viewed from a point on the positive y-axis. That's this matrix here. Okay. So you're rotating by the angle theta, but how do you work out the angle theta, or how do you specify that rotation matrix? Well, you need to look closely at a good, accurate diagram of the situation so that you can read off these entries of the rotation matrix in terms of the data of the situation. Okay, so we're focusing on this diagram here, diagram figure 6.10. So this shows the XZ plane. So we're looking at the XZ plane. Yeah, contort my hand. So we are looking at it from a point on the y-axis. So first of all, should confirm that, just to be clear. So here's our point D will be somewhere. Now, it's not necessarily on the XZ plane. It will be somewhere floating over there. So we can see two aspects. Remember, D is the vector from V to C minus V. Oh, sorry, it's from the viewpoint to the center view. Yeah, that's right. C minus V, yeah. I was just doubting myself that I thought I wrote down V minus C before. So that's the actual, well, what is that line we're seeing? What exactly is that line? That's we're seeing a view of this line here, which is the line from the origin to the center of view. But now we're just looking at the XZ plane. So we're just looking at the projection of that line down onto the XZ plane. So if we're examining this triangle here, we want to think about, let's call this W. Let's call that length W. We want to think about what exactly W is. Now, these other two sides of the triangle, we know exactly what they are. They're going to be dx and dz. Those are the x and z coordinates of the vector d, which themselves are going to come from the x and z coordinates of the vectors c and v. So we'll consider dx and dz as part of the data as well. Okay. So V and C are part of the data, so the components of D are as well. And this W is simply this hypotenuse side here, so we can easily say what that is. W is just the square root of the sum of squares, dx squared plus dz squared. Okay. Again, we've got this quantity now in terms of the inputs. Okay. And what angle do we want to rotate by? Well, it's whatever this angle is here, theta. We want to rotate around the y-axis, coming out of the page, by an angle theta, because that will send our vector d onto the z-axis, so it'll be lying on the yz plane then in 3 dimensions. We're going to make the x-coordinate of the center of view. We're going to make it be 0. So the center of view will be in the yz plane. Okay, so what we're doing here is we're solving this exercise 6.1. So what we need is basically cosine theta and sine theta. So cosine theta, we can see now adjacent over hypotenuse. That's going to be dz over w, isn't it? And sine theta going to be opposite over hypotenuse. That's going to be dx over w. Okay. Again, just emphasizing how the ingredients for the rotation matrix are coming from the data of the setup. So everything really is flowing, everything there is obtained from C and V. So we now have the necessary rotation matrix Ry given in terms of the data C and V. Because Ry features zeros and ones and these cosines and sines, which here are in terms of the D's and W's, but the D's and W's are coming from the C and V. Okay. So the matrix Ry would be dz over w. It's just the actual matrix you're going to have to use, minus dx over w. 0, 0, 1, 0, 0. And a dx over w. 0, dz over w. 0, and then that last row is always 0, 0, 1 for one of our homogeneous transformation matrices. So that's the first rotation we need. So that will rotate our point D here onto the z-axis. And let's say it goes to a point with position vector d prime. So now the center of view is at d prime. Okay, but we're rotating all the objects, so the center of view will still have the same relative position to all the vertices and objects in the environment, because we're rotating absolutely everything in the environment. Okay. So if you look over the page then, we can then see the triangle for determining the second matrix we need. Everybody got that one? So the second matrix we need is going to come from this diagram. And so we're then looking at it in the YZ plane. The center of view is now at this vector d prime. There's some angle here, phi, which we want to rotate away. We want to bring d down onto the z-axis. Now, but what are the sides of the triangle? Well, there's this vertical side here. And what is that vertical side? That vertical side is the same, isn't it, as the original dy quantity? Because what was the rotation we just did? The rotation we just did was rotation around the y-axis. Now, y, remember, is the height in the environment. So we rotated the ground around the vertical axis, the y-axis. So that won't have changed the y-coordinate of the vector d prime. It will have been the x and z coordinates that will have changed. Okay. It will have been the x and z coordinates that will have changed. This horizontal side of the triangle, and what is that? Well, that is the quantity w, which we had from the previous diagram. This is the previous diagram. When d gets rotated onto the z-axis, it's this length, it's this radius w, which is going to be the z coordinate of the point, isn't it? When that point has gone onto the z-axis, from my elbow up to my fingers, that's the length w. So that's the z coordinate of the vector d prime. So that's the setup that we're looking at. Again, we can obtain cosine phi and sine phi as we need it. Cosine phi is going to be adjacent over, well, we need this hypotenuse here. Very good point. I was about to recalculate the hypotenuse, but I don't need to because I know it's d. This is still, this line here is still the radius. Yeah, we're only doing rotation, so we're not changing. We're only doing rotation, so we're not changing. Yeah, that's the whole, because that vector, yeah, it's because that vector is now lying in the YZ plane. So this isn't a projected version of the radius we're looking at. It is the actual radius. So it is just the magnitude of our original vector d. So that hypotenuse side is the magnitude of d. So the cosine becomes this, and the sine of phi becomes dy over magnitude of d. A magnitude of d, of course, is part of the data. That's just the square root of the sum of the squares, dx squared plus dy squared plus dz squared. So you should just, yeah, just make sure. I only kind of realized it there. This is the actual radius line we're looking at, because the vector d prime in the environment, the vector d prime is in the yz plane. And we're looking at the yz plane here. So this is the unadulterated radius vector here. Whereas in the previous diagram, okay, we were looking at the position vector d, and that, okay, maybe that looks like the radius d, but no, because we're only looking at the xz plane, and this d point wasn't necessarily in the xz plane. It could have been up here, it could have some positive y coordinate. So this line on the diagram you're looking at is the projection of the actual radius. So that changes its length when the actual radius gets projected down to here. So that's why we have this we're only taking account of 2 of the components. We're missing out the y component there. So this is the cosine phi and the sine phi in terms of the data. So that can go into the rotation matrix Rx then, which is that form. So you can write down the matrix Rx then, okay? Because you have all the components. So we've now found the 3 transformation matrices: the T, the Ry, and the Rx. So we just, to get the overall transformation matrix, remember this principle: if you've got matrices for the individual transformations, when you compose them, the matrix representing the composition overall is just the product of the matrices. But in this, the product must be constructed in the order which matches the order in which you compose the functions. Okay. So this process we've been describing is translate first, then rotate around y, then rotate around x. So the matrix product we form is the one corresponding to that. Because remember, these matrices work by multiplying the column vector, putting it on the right of the matrix. So we apply T first, then rotate by y, and then rotate by x. Question? Dave, yeah, so I've taken these diagrams from last year's notes, so that's why, well, they put W there, but yeah, so change that, so that's magnitude of D. Yeah, sorry. Just use magnitude of D for that hypotenuse. Figure 6.11. Okay, so this matrix product then gives us the overall transformation matrix. Okay. So it's related to the kind of the rotation sequence product. Remember before where we were describing the transformation matrix for a general rotation around a general axis in 3 dimensions. So you'd far more matrices there because you wanted to just rotate around that other general axis, and we did that by bringing everything to the origin, shoving everything around till it's on the z-axis, then rotate around the z-axis, and then shove everything back. But here, of course, we're only doing kind of half of that process. We want to drag everything to the origin, get the center of view, rotate that a couple of times so it's lying on the z-axis, and then leave it there, ready for projection onto the screen. That's why this rotation sequence product is only about half as long as the previous one. Okay, right, we better leave it there for this morning.